So this is with my supervisor, Con Klassen, and I would like to talk about better random number generation for Haskell. So I guess this doesn't work. Let's consider this quick check property. We first define a type that will be numbers from 0 to 13, and then we define a very simple generator for this type, and let's say we want to test this very simple property. So we take two numbers. So the first argument is a pair, and we don't care about the first component of this pair. The second component is a number, another number, and we want to check if they are always different. And what should happen here?
Check should fail.
Well, too bad, it succeeds. And the reason for why it succeeds is that the standard random number generator for Haskell has a problem. And I won't talk exactly about what the problem is, but the problem lies here. This is a fragment from the system random module and a comment from the splitting function. So what are splittable random number generators? Splittable random number generators allow us to generate random numbers, but also to split the seed into two independent generators. So the program that is using it may create any number of new generators by executing the split operation. And this is important for generating random lazy data structures, for example, infinite ones, because then generating one part of the data structure doesn't depend on generating the other. So we can actually have a real lazy generator. And so far, there has been not so much research about how to make splittable random number generators. And the way it was done in Haskell was that a known linear random number generator has been taken from the literature, and splitting has been added on top of that in some way. But it's not so easy to add splitting to a linear random number generator, because there are actually very few things, very few formal properties that linear random number generator has. So first the most important one is the period, which is the length of the sequence that it generates, the seed size, and also a generator is supposed to pass some statistical tests. But it's not really defined what these statistical tests are. There are quite a few standard test suites with these tests, and they are quite good, but it's still not. You don't really know what is in this test suite. And of course, period is usually 2 to the power of 2 to the number of bits in the seed for good generators. So let's consider a splitting tree of a generator that we would like to have. So the program that is using this generator may execute any number of splits, and then in some of these nodes it may start generating random numbers. Oh no. And the problem, so one problem is that you see that very quickly we will have to start repeating the seeds. And secondly, there might be some seeds which generate related random numbers, which is what happened in our example. And this is not at all what we can this is not at all what we can solve by just using these properties, which is why we need much stronger properties, which are provided by cryptography, and in particular by crypto block ciphers. So there's a very strong property of crypto block ciphers is that there's no practical program that can distinguish between randomness generated by the cipher and true randomness, which is exactly what we need. So here's how we would create a linear random number generator based on a block cipher, and these two elements are not related to each other if the block cipher is good. And here's how we could generate, how we could create a splittable random number generator using a block cipher. So in this part of the split, we have the key and we have a counter, and when we go right, we just increase the counter. Whereas where we go left, we encrypt I with the key k and get a new seed. I see a 0 here. So this idea has been suggested by Barton Smith in his communication with Simon Peyton Jones. And after a couple of tricks that we applied by using additional things to speed up splitting, this is the numbers that we got. We managed to create a good random number generator based on a crypto block cipher, which is only 24% slower than stdgen. And actually very few time is spent in the block cipher that we are using, very little time. And it's actually faster for linear generation than stdgen, but still not as fast as the fastest generators available.
All right.